Okay, welcome everyone. One more Thursday to the corresponding lecture of our P&S on heterogeneous systems. And today, after having introduced the CUDA programming model, the memory hierarchy, and also some important performance considerations, we are going to talk about one of the important parallel patterns that is called the parallel reduction. It's probably one of the most important patterns for parallel computing, and also it's a very interesting exercise in GPU programming about how to optimize code in different ways. So very briefly, as we always do, recap on what we have covered in the previous lecture or in several of the previous lectures. As I said in the previous lecture, we talk about some GPU performance considerations. Remember, first of all, that when we are writing a program for an heterogeneous system with CPUs and GPUs, we will normally execute the serial code or the modestly parallel code on the host and the massively parallel sections of code on the GPU. Here you can see one example. Remember that inside each, when we launch a kernel, what we are doing is launching what we call a grid of threads, and these threads are organized into blocks. So we normally define what we call the execution configuration that consists of the number of thread blocks in the grid and the number of threads per block. We also discussed in one of our lectures the memory hierarchy of the GPU, and remember that individual threads have access to their own local variables that are stored in the register file, in the corresponding the registers that have been assigned to each of the threads, and then threads can share data and communicate using an on-chip scratchpad memory that is called shared memory in the CUDA programming model. All threads of different blocks have access to global memory and also a constant memory that also resides in the memory of the device. Remember that in the last lecture, we were talking about performance considerations, and one of the important things that we mentioned is that it's important to have, if not 100%, but at least a relatively high occupancy value. And the occupancy is the ratio of active warps per GPU core or per SM or simultaneous streaming multiprocessor to the maximum number of warps that can run on the GPU core or the streaming multiprocessor. And here you can see one example of the effect that causes some let's say high occupancy or a low occupancy. If we have very low occupancy, we won't be able to hide some long latency operations, such as, for example, accesses to the global memory. Related to the access to global memory, remember that it's also important to try to optimize these accesses by coalescing the accesses. Essentially, the memory coalescing consists of having multiple threads accessing together, those threads that access together to memory, those threads that belong to a warp, accessing data in the same DRAM burst, because this way the request can be satisfied with a single DRAM transaction. In case that the threads of the same warp don't access data in the same burst, then we will have what we call the uncoalesced accesses, or also called memory divergence. And essentially, as you may remember, in this example with two matrices, we are going to see coalesced accesses when consecutive threads access nearby memory locations. For example, if in successive iterations, these threads 1 and 2 access elements in the same row, they will be accessing data that belongs to the same DRAM burst, likely the same cache line as well, or several consecutive cache lines, and the accesses will be much faster and much more efficient than if we access in a different way. For example, here we are accessing by rows. In each iteration of the algorithm, thread 1 and thread 2 are accessing elements in different rows. So there is a stride between the accesses of thread 1 and thread 2, and this makes that the access is much more inefficient because data doesn't come from the same DRAM burst, essentially. But we also talk about the possibility of optimizing the accesses to memory by taking advantage of the shared memory, of the on-chip scratchpad, as you may remember. So in the case of this matrix MD that is accessed by rows, one thing that should definitely optimize the performance of our program is the partitioning the matrix into tiles, loading these tiles into the scratchpad memory, and this way we will likely access more efficiently because we avoid all the issues related to the memory and coalescing. That said, remember that we should also be careful when accessing when accessing the shared memory, because we may incur into bank conflicts. And the last thing that we covered in the previous lecture was another important performance consideration, that is the SIMD utilization. Essentially, the SIMD utilization refers to the number of lanes or the number of threads in each warp that we are really making use of when we execute one instruction. Remember that one of the key advantages of the SPND programming model that GPUs use is that it's relatively easy to write code because we don't have to worry about how we launch, how the threads execute the different instructions. We are free to schedule, to have threads executing different control flow paths, and that's certainly doable, programmable, and certainly is going to be executed by the hardware, the underlying hardware. What's the problem? The problem is that for the SIMD hardware or for the GPU to be able to execute these different paths, as we have in this figure, path A and path B, we need to make use of a mask. And what this mask does is essentially defining what are the threads of the warp that are going through path A or through path B. In the end, what happens here is that if we have branch divergence, that is, if threads belonging to the same warp go through different paths, we will end up executing twice the number of instructions, right? So this is what we call the branch divergence, or also called intra-warp divergence. And it's something that, even though it's supported by the hardware and we can write programs that suffer from warp divergence, we should try to minimize this divergence in order to obtain the most from our hardware. And you might also remember this more specific example where there is kind of a simple pseudocode here showing the intra-warp divergence. In this particular case, we have this if-else statement, and we decide that even number threads do this and go through the if path, while the remaining odd number threads go through the else path. What's the problem here is that the execution is going to be something like this. So we would be only using half of the threads in the if path and also half of the threads in the else path. So in the end, during the execution of the if path or the else path, we have a SIMD utilization of only 50% in this particular example. One thing that we should always try to avoid the SIMD underutilization or the warp underutilization is modifying our code in a way that obviously produces the same results, but we somehow try to avoid this divergence. And this could be a different mapping. In this case, what we are doing is assigning the computation in the if path to those threads that have a thread ID lower than 32, so they belong to the, let's say, warp 0, and the rest of threads go through the else path. And this way, we are in the if path, we execute threads that are consecutively numbered, so it's likely that they belong to the same warp and they execute all together, and we obtain 100% utilization here, and then do the same on the else path of the execution. And this, let's say, software modification or software optimization that we have performed here is also applicable to some important use cases, such as the reduction operation. And As I said in the beginning, today we cover this important parallel pattern that is reduction. But first of all, let's define what we mean by the reduction operation. A reduction operation reduces a set of values to a single value. That's essentially what a reduction operation does. The operation itself might be different. For example, an addition or a multiplication or obtaining the minimum or the maximum. These are possible examples. Important thing is that the operation itself has certain properties, what we call the properties of reduction. These reductions should have associativity, so it should be an associative operation, should be commutative, and should have a well-defined identity value. In this lecture, we are going to take sum, the addition, as or running example. And as you may remember from the school, addition is commutative and it's also associative. Commutative meaning that A plus B is the same as B plus A. Associative means that if we have to add A, B, and C, the result will be the same. Either we first add A and B and then C, or B and C and then A, etc. And then the identity value, as you may know, in the addition is 0. Reduction, as I said, is a very important primitive for parallel computing. And for example, in the MapReduce programming model is one of the basic operations, as you may know. So how do we perform a sequential reduction? Let's say this is the most straightforward thing that we can do to calculate sequential reduction is to simply use a for loop to go through all the elements of the input array, and then one by one we start accumulating the values of in the input array. So it's as simple as a for loop where we go through all the elements of this input array A, and we add all these elements to some variable, in this case, this sum, which is the accumulator, where we store the partial results until we have the final result. The final result after having gone through the whole array N. Remember that it's important to initialize the variable where we are going to store the partial results using the identity value, which in the case of addition is value 0. And the interesting thing here is that because addition is commutative and it's associative, we can extract many different independent operations from here. What that means is that we can partition this for loop across many workers, across many parallel threads, and we can assign each of these threads one part of this for loop, have all of them calculating their own partial reductions, their own partial sums, and then finally reduce all these partial sums together in order to obtain the final result. So if we do that, what we would be implementing is likely a tree-based reduction. A tree-based reduction is essentially an iterative algorithm that goes iteration after iteration over the partial results that we have generated in the previous iteration and adds every 2 partial results until the point where it obtains a final value, right? So in the example of our array A, one thing we could do in iteration first is to have one parallel thread, for example, adding a element A0 and element A1 and obtaining some partial result that we will store in some temporary storage. We can also have another thread adding element A2 and element A3 and storing it in another temporary position in some temporary storage, and so on. In iteration 2, we continue. We could probably retire half of the workers that participated in iteration 1, because in this case, we only need to execute half the number of additions as we did in the previous iteration, right? So in this case, we will have one thread adding this element here and this value here that are in temporary storage, and again, storing the result in the temporary storage, and the same for the other pairs of values obtained or partial results obtained in iteration 1. And then we continue iteration 3, and finally in iteration 4, we obtain the final result. So notice that in this particular example, we have calculated the reduction of 16 elements. This n in this example is 16, and we took four iterations, right? So in the end, for any number n of input elements that we have to reduce, with a tree-based reduction, we need a number of log n iterations. So we are clearly accelerating the execution of this important primitive, the reduction, by parallelizing using this tree-based reduction. But now we define the tree-based reduction in a generic way, let's say. Now let's see how, or let's start discussing how we are going to do this on the GPU. So remember that what we normally do in GPU computing is that we partition the whole problem into different chunks that are assigned to different thread blocks, right? In this specific toy example, we are going to use, we have a small input of only 16 threads. So only 16 input elements. So we are going to use 2 thread blocks. And these 2 thread blocks are composed by a number of threads, probably 8 threads in this example. And these threads belong to some warps, right? I'm assuming in this toy example that the size of a warp is only 4 threads, not 32 as in the real architectures, right? So block 0 is composed by 2 warps in this case. Block 1 is also composed by 2 warps in this case. So, and then we proceed, right? So in the first iteration, we would have 1 thread belonging to this warp 0, performing this addition and storing the partial result somewhere in some temporary storage. And you can guess what this temporary storage is on the GPU core, right? It is either shared memory or registers. We will start today or explanations talking about, or implementations talking about shared memory. And then we have another thread that performs the addition of these 2 elements and obtains some partial results, some partial sum, and the same in warp 1, and also the same in in block 1 as well, right? And here we have to identify, or we have to notice that there are some boundaries, right? Because there is this part of the array, and these partial sums here are computed by warp 0 of block 0, and these other here are by warp 1 of block 0, and so on. And here we also see that there is kind of a boundary between the computation being done by block 0 and the computation being done by block 1, right? Remember that all these threads that are running together in the same warp, they execute in lockstep. But threads belonging to different warps in the same thread block don't finish their computation in the same cycle. So this is why from time to time, not from time to time, after each of the iterations of the tree-based reduction, we need to synchronize all threads that belong to the same block in order to make sure that all threads that are participating in the reduction belonging to different warps have already computed the addition and stored the corresponding partial sums in the temporary storage, let's say in shared memory, right? So that's why we need to synchronize internally to each thread block after each iteration. And this is what we do with the Sync Threads API, as you may remember from our previous lectures. Then we go to the next iteration. Again, remember as well that half of the workers here, half of the threads will retire, because in this case, we don't need to compute so as many additions. In this case, the number of additions is half the number of the previous iteration. And then after this iteration, we again have to synchronize. And then it comes the next iteration. And if you observe here, we are obtaining one final, let's call it final, but in reality it's a partial sum for block 0 and another final partial sum for block 1. And now remember that there is no way to synchronize threads belonging to different thread blocks other than terminating the kernel, right? That's the traditional way or typical way of synchronizing different thread blocks. The reason is that we don't have any certainty about when the thread blocks are executed. I may launch in my for my kernel 1,000,000 thread blocks, but my GPU might only have a single core. And if my GPU, or let's say 2 cores. So what that means is that I'm going to time share the GPU cores, not really time share. I will schedule some thread blocks, as many as I can on the available hardware. And when they finish, they will retire and I will schedule more thread blocks, right? So I don't have any certainty about when this block 0 or this block 1 are going to be executed on the hardware, right? So the only way to make sure that all threads and all thread blocks involved in this tree-based reduction are done with the iterations that they can do by themselves is to perform some sort of inter-block synchronization. And this is what we typically do by terminating the kernel and probably launching a new kernel. That's the only way we can synchronize. And actually, in this particular example, we can do this final reduction in 2 different ways. For sure, we need to terminate the kernel. And after that, we can either reduce the final, these partial sums here on the CPU. And this can be probably a good idea if the total number of partial sums generated by the individual blocks is not too large and there's not so much parallelism, so the CPU can do well. Or if we have launched, let's say, millions of blocks and we have millions of these partial sums here, it might be better to launch a new reduction kernel on the GPU. So it could be like a recursive execution, right? Because we are going to use the same kernel. In this case, the only thing is that the total size of the input array would have been reduced by the size of the thread blocks that we used in the first invocation of the reduction kernel. And then there is a last way of doing this inter-block synchronization, that is using atomic operations in global memory. In this case, we are not terminating the kernel. Instead, after thread block 0 has computed this final value, we will use one atomic operation to accumulate this value to a final value that resides in global memory. So when block 0 computes this, one thread of this thread block takes this value and by using an atomic addition adds it to the corresponding global memory value, global memory element that is going to store the final reduction result. And then when block 1 finishes with the computation and obtains this final partial sum, we will do the same with the atomic operation. And we are going to talk a little bit more about atomic operations soon. Let me know, guys, if you have any questions so far. Feel free to stop me as well, even if I speak quickly. Okay, so more or less, we understand already how we are going to parallelize, or how we need to parallelize this tree-based reduction on the GPU, essentially partitioning the whole input array into different chunks that are assigned to different blocks. And then we perform iteration after iteration. We calculate the partial results. Half of the threads will retire after each iteration, and we need to synchronize between iterations, because we need to make sure that the partial results, these ones here or these ones here, are already in the temporary storage, let's say in the scratchpad or shared memory. And then, yeah, this is the calculation of the final reduction result. Okay, you may remember also this slide from the previous lecture. We discussed very briefly how to do a naive mapping of this tree-based reduction using the one GPU kernel, right? In the naive mapping, what we do is using only even numbered threads, thread 0, 2, 4, 6, 8, and so on. And in the first iteration, the computation that we assign to each of these threads is the addition of 2 consecutive elements. So for example, first iteration here, thread 0 adds element 0 and element 1, and thread 2 adds element 2 and element 3. And after that, we obtain some partial results that we store in shared memory, and we retire half of the threads and we continue the execution. So remember that we need to use sync threads here in between to make sure that all these values, these partial results, are already in the place where they have to be. Half of the threads retire, in this case, the green color threads retire, and now this thread 0 adds this partial result plus this partial result and obtains 1 partial result, and so on. And this way, we can compute after log n iterations, we would be done with the reduction of the elements that have been assigned to one particular thread block, right? And you may also remember this code that is the code corresponding to the previous slide, to the previous naive mapping. We essentially here have a for loop. So first thing that you have to consider here is that we have an input array A, and before executing this for loop, which represents the parallel reduction, the tree-based reduction, we have loaded the values, the corresponding values of the array A in global memory into the shared memory. We do this because we know that shared memory is closer to the core, so it makes sense to directly use shared memory and use it as much as possible, especially in this kernel as well. There is a lot of data reuse, as you can see, because all partial results that are calculated in one iteration are reused in the next iteration, right? So we assume that all the elements of A are already loaded into this partial sum array that is in shared memory, and then we start the execution of the for loop. Notice that the for loop goes, it's the index of the for loop is this stride that goes from 1 to the size of the block dim, and in each iteration, we multiply the stride by 2. Then these sync threads here, it's necessary to make sure that the values that are stored in shared memory are already there after the computation, either before the beginning of the for loop or in the loop body. And here we have this if statement that determines what are the threads that are going to continue with the execution. So if you think about this code, you will see that, well, we are going to assume in this case that we are using one thread block with 4 warps. And in this toy example, each warp has 4 threads, as you can see. But if you check what's the utilization for the very first iteration here for a stride equal to 1, you will see that here the if statement or the if path is only executed by even number threads, right? So that's because what we have here in parentheses is T, which represents the thread index modulo 2 times the stride. So 2 times the stride is 2 in this case. So the thread IDs that fulfill this predicate here are only thread ID 0, 2, 4, and so on, right? So half of the threads are already idle in the beginning of the execution of this for loop, this tree-based reduction. And it's even worse when we go to stride 2. When we go to stride 2, you can already see that only 1 of every 4 threads in the same warp is active, while the other threads are idle. And when stride is equal 4, in this case, only 1 every 8 threads is active. Yeah, we have lows in the utilization here, and this warp 1 and this warp 3 directly retire. So we see that there is a lot of warp underutilization, especially here in the first iteration with the stride 1, and also in the second iteration with stride 2. How can we avoid this warp, or at least minimize this warp underutilization? Well, we already discussed this example in the previous lecture, and you may remember that the key idea was using as much as possible threads that belong to the same warp. So what we do is using neighboring threads, so threads that have an index, an adjacent index, as you can see in this particular figure, threads from 0 to 16, and we assign, and we can do this because the addition is associative and commutative. What we do is assigning different additions to each of the threads, but making sure that iteration after iteration, the threads that remain active are threads that are consecutively numbered. And this way we maximize the utilization of the corresponding warps. So in the first iteration, thread 0 adds element 0 and element 16, and thread 1 adds element 1 and element 17, and so on. We store these partial results into shared memory, then we synchronize, and then we retire half of the threads. In this case, we retire all these threads here, but all these other threads remain active, and we keep adding partial results until we are done and obtain the final value for this particular thread block. And this is the code that exactly executes the operations that we have seen in the previous slide. In this case, with respect to the code with low SIMD utilization, we have to change this for loop, and we also have to change the if statement. But what we do, as you can see, and we essentially partition the input array in the same way. We are using 4 warps, and each of the warp has 4 threads. Yes, we are assuming a block dimension in this toy example. We are assuming a block dimension that is equal to 16. So that's why a stride starts with the value 16. And then in the next iteration, we divide a stride by 2. It's the same as shifting 1 bit to the right. And in this case, half of the threads retire. But the good thing is that the threads that remain active are consecutively numbered, and this makes that they belong to the same warps. There is also one more assumption here, is that in this specific code, instead of reducing only 16 elements, because the size of our thread block is 16, we are reducing 32 elements, right? So that's why in the very first iteration, stride 16 is this thread 0 is going to add this element A0 and also the element that is here, which would be element 16. So it's exactly what we can see in this line of the code, right? If a stride is equal to 16, partial sum 0 is incremented by partial sum 0 plus a stride, which is 16, right? And that's why in the very first iteration, all threads are active. But then in the next iteration, with the stride 8, half of the threads retire, but the threads that retire belong all to the same warps. So notice that these 2 warps here remain completely used, remain with utilization equal to 100%. And in the next iteration, stride 4 is the same. All threads of warp 0 are active. So warp utilization is maximized. But there are ways of optimizing this code even more. I mean, it's really fascinating, the amount of possibilities that we have to optimize this important code. And one of the things that we can use, or one of the functions or instructions that we can use to continue with the with optimizing this code is using what we call the warp shuffle functions. And I take the opportunity today to introduce these important operations that didn't exist in the very early generations of CUDA GPUs, of NVIDIA CUDA GPUs, they started at some point, if I recall correctly, it was with the Kepler architecture back in 2012. And since then, we have seen many programs and many different applications being optimized by using these warp shuffle instructions. Let me explain you what they are about. So the warp shuffle instructions are instructions that allow threads in the same warp to share data with other threads in the same warp without using shared memory or without using sync threads. Remember that when we started with this course, or when we started talking about GPU programming, we said that the only way for threads belonging to the same thread block to share data and communicate is by using the shared memory. And we also know that if these threads belong to different warps, we have to use sync threads to synchronize the different warps, make sure that everything before the sync threads API has already been executed, right? So what's the problem here? The problem is that accessing shared memory is fast, but it's not as fast as accessing registers. And also the sync threads operation also takes a few cycles, right? Because when the first warp reaches to the sync thread, it has to wait for the other warps to reach to the same point, and then another warp, and then another warp, and so on. And this is kind of a waste of cycles, right? So if we can avoid the use of these sync threads as well, we would be likely optimizing our program as well. So that's what warp shuffle instructions or warp shuffle functions enable: sharing data that belongs to one thread, that resides in the registers, in one or several of the registers of one thread, share these values with other threads that belong to the same warp. And there are different flavors of this warp shuffle function. The first of them, I mean, it's some of them that have relatively different functionality. The first of them is this shuffle sync. As you see, it has three. Actually, there is a fourth parameter that it's optional, so that's why I'm not including it here, but you can find all the details in the CUDA programming guide. So the parameters are a mask that defines is a kind of a software mask, like a bitmap, that decides what are the threads that belong to the same warp that are really going to execute these operations. Some of the threads might remain unused because of the programmer decision, for example. What's the variable, what's the value that we are going to share with a different thread, and what's the source lane, which means what's the source thread that belongs to the same warp, right? So, for example, if I have, say, a warp of 32 threads, thread 0 might execute this shuffle sync, and this source lane might be equal to, let's say, thread 1 might be equal to 1, or might be equal to 6. So what that means is that thread 0 is going to receive the value contained in this variable, in this register bar, that comes either from lane 1 or from lane 6. So we are indexing a specific lane and a specific thread in the warp to bring the data that we need in the corresponding thread. And there, as I said, different flavors. Another way of doing the similar thing is using the shuffle up sync. In this case, we are not giving a specific thread index or lane index, but we are giving kind of a delta, right? Which is the distance from this thread to the thread that we are getting the value from. For example, if delta is equal to, with this shuffle up sync, we would be reading the bar value of a thread that is the thread ID minus delta. So for example, thread 2 is getting the bar value of thread 0 if delta is equal to, or thread 3 is getting the value of thread 1 if delta is equal to. And same thing, we can do it, but in the opposite direction with this shuffle down sync. And there is another way of doing the shuffle operation, that is this shuffle XOR sync, but in this case, obtains the lane from which we gather the result by performing the bitwise XOR of this lane mask and the own lane ID or thread ID within the warp of the corresponding thread that executes this. But today we are going to only use this shuffle down sync. In later lectures, we would likely discuss other uses of these shuffle instructions. And by the way, I want to give you an intuition of how these shuffle instructions work. And to do so, I'm going to base my explanation on one figure that I obtained from a patent that was filed several years ago. But I think that it's kind of interesting figure because it can allow us to understand how shared memory or how the register file is being accessed by the different lanes, and also guess how the shuffle instructions are executed. One clear disclaimer that I want to make here is that I don't know how the shuffle instruction is internally being executed in real GPUs. The only thing that I'm going to explain you next is an intuition of how this will how this likely is being executed. In the figure, you can already identify the processing engines that are the different SIMD lanes that take part of the GPU core. You can also identify some SRF banks that are probably equivalent to the shared memory banks. This SRF means shared register file, but this is essentially the same as the shared memory composed by B banks. As you may remember, a typical number for this B is 32 in current architectures. And you can also identify here these LRF lanes, LRF meaning local register file. So these are essentially the registers that are assigned to each of the individual processing engines or SIMD lanes that you see in the figure, right? So these are the registers for this processing engine 0. These are the registers for this processing engine 1, and so on. And the one thing that the patent explains is how to read from one shared memory bank. So for example, if we want, or this, the lane, the thread executing in this lane 0 wants to read some element, some value that resides in this shared memory bank, number with number 2, the way of doing it is by using this interconnect that we have in the middle, right? It's kind of a crossbar. And the way that we read is by accessing the value through the interconnect, then it goes to the processing engine, and this output here is connected to this input here, and we finally write into some register in the register file, right? So this is a read from shared memory. If we want to perform a write to the shared memory is something similar. We have this register here that belongs to lane 1, and we want to write this onto the shared memory bank, in this case bank 2, and what we do, or what the lane 1 does, is surrogating or asking this processing engine to perform the write onto the shared memory bank, as you can see. And based on this, which is what this patent explains, I can guess that one potential way, or one possible way of implementing the shuffle operations within a warp is doing something like this. We want this lane 1 reading one value that is contained inside a register of a different lane, in this case lane 0, and what we could do by using again this internal, so this interconnect is accessing the value in the register, moving it through the interconnect, through processing engine 1, and finally writing it into the corresponding register of lane 1. So this is, as I said, one possible way of implementing this kind of shuffle operation. As I said, I have no certainty about how this is really implemented, but I just wanted to give you this intuition for you to understand what these shuffle operations are. And by using shuffle operations, we can optimize the code that we created before with this high SIMD utilization. Notice that after this third iteration with stride 4, we start having threads that keep retiring iteration after iteration, but these threads now all belong to the same warp, to warp 0. So this is the next iteration for stride equal 2. This is the next iteration for stride equal 1. And one thing that I want you to notice here is that all these threads, all these 4 threads that are executing these these 3 iterations belong to the same warp. And because they belong to the same warp, they can use warp shuffle instructions to communicate, right? And this way, they will be able to avoid shared memory accesses and sync threads that are more costly than the warp shuffle or instruction, right? And that's essentially what we do in our code. And actually in this slide, you can see the let's say complete code of the reduction operation or the reduction kernel using in this case warp shuffle instructions. And let's talk about it. I mean, it's first of all the reduced kernel with the input parameters. We have this float input as a global memory array that contains the input array that we want to reduce. These float partial sums is where we are going to store the partial sums coming from each of the individual thread blocks, right? Don't get confused by the fact that we have used also partial sums as the name of the shared memory array in previous slides. These partial sums here is in global memory, is the output array in global memory, and this is the size of the input n. So in this implementation, the first thing we do is assigning to each thread block, we are going to assign twice the size of the thread block elements. So to each individual thread block, with block index x, we are going to assign and this thread block has a size block dim x. We assign to this thread block 2 times block dim elements. And this allows us to do one more optimization, pretty simple thing, but pretty useful and efficient thing is by when loading the data into the shared memory, and notice that here we are declaring the array in shared memory input s. When loading the data into shared memory, instead of loading one individual value and then start the reduction, what we can do is already read 2 values from the input array, we add them, and we directly, we are already doing one of the additions that we have to do to obtain the final reduction result. So we load this first partial sum into this input S, and then we synchronize all the threads, and then we start with the reduction tree in shared memory, same as we have seen in previous slides. Remember that the threads that are active are those threads that are numbered, that have an index lower than the stride, the value of a stride in each of the iterations. And here we perform the addition, and after that, we synchronize to make sure that all threads belonging to different warps in the same block are done with the execution of this addition here, right? And but notice there is a difference with respect to the previous code. Is in the previous code, this stride was so a stride was getting reduced, divided by 2 iteration after iteration until it was equal to 1. In this case, we stop earlier. We stop when a stride is, so we continue doing the execution of this for loop until while a stride is greater than warp size, than the size of the warp that, remember, is 32. In that case, at that point, we can start using shuffle instructions. Why is that? Because at that point, only threads belonging to the same warp remain active in these in the execution of this kernel. So we can start using the shuffle instructions as we do here. And as you can see, we don't have to anymore go to shared memory or synchronize. And in this case, we are doing this with the shuffle down sync. For every thread executing this, we are fetching, we are gathering the content of the variable sum of the lane that is numbered as the current lane plus stride, right? So this is why it's shuffled down. So if this is being executed by lane 0, by thread 0 in the warp, and a stride is equal to 8, thread 0 by using this shuffle down sync is getting the content of the sum variable in the lane 0 plus stride, which is equal to 8 or equal to 16, or depending on the iteration where we are, right? And after that, the final thread, in this case, thread 0, can store this partial sum into the partial sums array in global memory that will be later reduced by one of the different ways that we discussed before. Maybe we will terminate the kernel and launch a new reduction kernel. Maybe we will terminate the kernel and we'll move all the partial results to the CPU and reduce them there. Or maybe we can already replace this here, this store operation here, by an atomic addition and in global memory. And in that case, we are directly computing the final result in global memory. And by the way, I was talking about atomic operations, about the possibility of using atomic operations. And now let me introduce you to the atomic operations or atomic instructions. CUDA provides atomic instructions to share memory or to global memory. And what they do is performing a read, modify, write operation atomically. So if I have one thread block or one warp composed of a number of threads, and each of them execute an atomic operation on the, let's say, same position, same element in shared memory or in global memory, by using atomic operations, I have the certainty that the final result will be correct, because all of the threads are executing read, modify, write operations atomically. We are going to see an example of that, or actually several examples of that. And here you have the different arithmetic instructions that CUDA supports. It supports arithmetic functions like addition, subtraction, maximum, minimum, etc. This is the typical syntax, in this case for an atomic add. This here is the pointer to the specific position in shared memory or global memory that we are going to update. This value here is the value that we are going to add, in this case, to this position in memory, and this atomic add function returns the old value that is stored in this position. And same thing, we also have atomic bitwise functions like AND, OR, and XOR, and the atomic operations exist for different data types as well. In the example, we were talking about integers, but they also exist for unsigned integers, long, and also floating point. Okay, so yeah, I explained you that the execution of atomic operations is serialized, because we should make sure that the read, modify, write operation is performed atomically. And what that means is that we may have two threads, let's say thread 0 and thread 1, and they execute one atomic addition on two different elements, in this case in shared memory, for example, element 0 here and element 2 here. And the good thing is that there's no conflict here, because they are updating different memory locations, so they can read at the same time, they can modify the value, let's say adding 1 or adding 6 or adding whatever, and then they can write back to the same position in shared memory. They can do it atomically, and there is no problem here, no conflict here, because they both are accessing different shared memory locations, right? Or different global memory locations in the case of global memory. And in some other case, it might turn out that in both threads in the atomic operation need to update the same value, for example, this element 2. So in that case, we will have a conflict, and as you can see, the total latency of the operation will increase due to the serialization of the execution. So if there is no atomic conflict, we can have atomic concurrent updates. If there is atomic conflict, we will have serialized updates, and will for sure affect the final performance. if you think about it, we could directly write the reduction kernel by using only atomic adds, right? Same as these thread 0 and thread 1 are accumulating some value here in this element 2. We could do that with all threads that belong to the same thread block, for example, and accumulate all the values on the same shared memory location, for example, and in the end accumulating into global memory. That's something we can do, but it's something that we don't usually do. Why is that? Because we are serializing the execution, and we are in that case we would be losing all the advantage of executing multiple threads at the same time, right? Because atomic operations serialize the execution. So that's probably not a very good idea for the reduction, but still atomic operations can help in some cases. Atomic operations are also very useful for other computations, like for example, histogram calculation. You might be familiar with histogram calculation. Essentially consists of counting the number of occurrences of a particular value in an input array. For example, if we have an input image, we may want to count what is the number of pixels that have brightness equal 0, what is the number of pixels that have brightness equal 1, and so on. So that's how we create a histogram. If we want to parallelize the execution of a histogram, we'll have to do something like that. We distribute the input data across different threads, and then we tell these different threads to update the corresponding bins of the histogram. The problem with creating the histogram is that we may have different threads. For example, thread 0 and thread 2 belong to the same warp or belong to the same thread block that are reading different elements, but these two elements or these two pixels may have the same value, and they have to update the same histogram bin. If we don't use atomic operations here, the final result, the final histogram will be wrong. Why is that? Because we will incur in a data race, because these two, thread 0 and thread 2, read the value of the bin at the same time. They update this value independently, and then they write they both at the same time. And when they write both at the same time, they are not writing the total sum, but they are also writing their individual sums or updated sums, right? So we could incur in a data race, and that's why we need atomic operations here. But we are going to talk about histogram calculation in a later lecture. Today, we are focused on parallel reduction, and I'm going to show you one example of how we can use atomic operations in the parallel reduction. But before that, let me introduce you to one of the CUDA samples that is devoted to the parallel reduction. And the interesting thing of this CUDA sample that you can find in the CUDA SDK, and here you can find the link also here at the bottom of the slide, is that this sample shows us different versions that optimize one by one the previous version of the parallel reduction. And it starts from the most naive version, we call it version 0, where no whole warps are active. This corresponds to our naive implementation, where we suffer a lot of SIMD or warp underutilization. Then we have the next version where this SIMD underutilization is solved, but there are still bank conflicts, and then another version that solves the bank conflicts, and so on. You can see that there are also versions using warp shuffle instructions. So in the end, after these 7 versions, we have a highly optimized parallel reduction that clearly outperforms the initial version 0, right? If you want to learn about the specific optimizations that are applied to these 7 versions, I recommend you for sure checking the code, but also this presentation, which is already, it's an old presentation. I think it's from 2007, but it's still completely valid and I would say state of the art of parallel reduction on GPU. And if we compare the performance of these 7 versions, these some experiments that I ran several years ago with these are all old GPUs. This is from the Fermi architecture, Kepler, and Maxwell. And in these 3 plots, we are comparing the throughput, the performance of the 7 versions. So higher is better in these plots. And we compare the performance of the 7 versions on the 3 architectures. And as expected, because as I told you, each of the versions optimizes the previous one, we see how the overall throughput or performance improves over versions, right? Being the last one, version 6, much faster than version 0 and the previous ones. And one experiment I did here was replacing the tree-based reduction with shared memory atomics. I told you before that this is likely not a very good idea, because if you have, let's say, 128 threads belonging to the same thread block, and you replace the whole tree-based reduction with one atomic operation per thread, you will likely be serializing the execution a lot, right? And probably not obtain very good performance. But anyway, I tried this because I wanted to see how the atomic operations had evolved over the generations and how they had improved from the Fermi architecture to the Maxwell architecture. And that's what I did here, defining 3 new versions that I call 7, 8, and 9. Version 7 is essentially version 0, where the whole tree-based reduction is replaced by atomic operations. Version 8 corresponds to version 3, and version 9 corresponds to version 6. The code is not publicly available, but I'm pretty sure that from the CUDA sample, you can do the same experiment yourself. And if you compare these 3 new versions, 7, 8, and 9, compared to the original 7 versions, you will see something like this. The red bars represent the new versions, and which are actually pretty bad on the older architectures, because the atomic operations in shared memory were pretty unoptimized in these architectures. However, in the Maxwell architecture, where NVIDIA already included new hardware to support the atomic operations to share memory, we can see that the performance is really good. Actually, for example, version 7, which is version 0 with atomic operations, is way faster than the original version 0. Version 8 also outperforms version 3, and even version 9 is essentially as fast as version 6. And what I'm just trying to show here is that there are many different ways of implementing the parallel reduction. We have seen that we may use shared memory. We can also use warp shuffle instructions. We can also use atomic operations. And each of these different implementations may have different advantages. For example, one advantage of using atomic operations in this case is that we can reduce the lines of code as you can see in this plot here. If you compare this version 9 to the actually 2 versions 6, because there are 2, one of them uses shuffle instructions and the other don't, you can see how much we can reduce the total number of lines of code. And similar reasoning or similar strategy can also be applied to other codes as well, right? And in the end, the atomic operations, even though they might have the drawback of lower performance or the serialization that I mentioned before, they can allow us to write code that is much more compact with less lines of code, and hopefully due to the advances on the hardware itself, as we saw in the Maxwell architecture, we may still obtain quite reasonable and good performance. And that's actually what we did in one of our papers presented in CEO 2019, where we compared many different implementations of parallel reduction. Concretely, we tested 85 different versions of parallel reduction. As you can see, some of them using atomic operations in global memory, some of them using shuffle operations, shuffle instructions, others using atomic operations in shared memory, and so on. And in some cases, and also depending on the architecture, we see that some of the versions are faster than other. If you are curious about the actual implementation and about the final performance results, I would recommend you to take a look at this paper. But this is not the only way of optimizing parallel reduction. Another paper that I like a lot is this one presented at ICS 2019, where the authors implemented parallel reduction using the tensor cores. You might remember tensor cores, which are these small superfast cores that the GPU cores contain since the Volta architecture to accelerate AI applications and neural networks. These are designed to accelerate these type of applications because they are designed to accelerate the, let's say, most important operation for AI workloads and neural networks, which is GMV, matrix vector multiplication, and the matrix-matrix multiplication, right? And if you think about these operations, what we are essentially doing in GMV or in GEM, in matrix vector multiplication or in matrix-matrix multiplication, what we are doing is dot product operations, right? In matrix multiplication, as you may remember, calculate every single output element. We need to read one row from one matrix, one column from another matrix, and perform the dot product of this row and this column, right? And if you, so it's that's essentially what the tensor cores are good at performing, executing these dot product operations, something like this line that we have here. And it turns out that if all the values corresponding to either the row or the column are equal to 1, in the end, what we are doing with this line here is adding all elements A0, A1, A2, until AN-1 of array A. So if all BI are equal 1, the result of this dot product operation will be the sum of array A. So here you can see a very fancy and smart way of doing parallel reduction by taking advantage of the tensor cores. And I would recommend you take a look at the paper and see the performance results that are really impressive. And also impressive might be, I don't know, because I didn't test this myself, are the new warp reduced functions that the new Ampere architecture compute capability 8 support, because this new architecture includes native support for the warp white reduction operation. So by simply using these functions that we see here, for example, this reduce at sync or this reduce min sync, we can obtain or we can calculate the reduction of a number of values within one warp and use these for the implementation of more complex parallel reductions that span multiple warps or multiple thread blocks, right? But as I said, this is quite new right now. I didn't have a chance to test this myself. I'm also not aware of any recent papers that use these warp white reduction operations. Hopefully in the next edition of the course, we will talk and we will explain more details about them. And if you want to learn more, want to read the Programming Massively Parallel Processors paper, again, I recommend you chapter 5, concretely section 5.3, that talks about the two first implementations that we mentioned of the parallel reduction, and also this chapter 9 that talks about histogram computation, but gives also an introduction to the atomic operations. Anyway, as I said, we will talk about atomic operations in a later lecture again, because we will explain the histogram computation. And this is all for now. This is all from my side today. Guys, please let me know if you have any questions.
I have a question.
Yes.
For the warp access to the shared register, is it as fast as for the local registers?
That's a good question, actually. So you are asking if the warp functions are, so warp shuffle functions are as fast as accessing the own register, right?
Exactly, yes.
Yeah, well, in reality, it's a little bit slower, right? Because if one thread, let's say thread 0, accesses one register that has been assigned to its lane, the value is already there, so you can directly use. And this essentially takes a single cycle to access that value. So if you have to read from a register that belongs to another thread and bring it to your own register, and after that use it, this whole operation is going to take a little bit longer, right? You may remember from the lecture where we talk about the memory hierarchy that I said something like access to the access to registers take one cycle, access to shared memory takes around 5 cycles or so. So the question is, how many cycles does the warp shuffle instruction take? Long time ago, when the warp shuffle instructions appear in the Kepler architecture, I remember to have run my own experiments to figure out what was the latency of these warp shuffle instructions. And I remember that it was something around 2 cycles. But again, disclaimer, I can tell you and I can imagine that they are faster than accessing the shared memory, but I don't want to give you an exact number of cycles. But yeah, in the end, if you apply this to your program, you will see a lot of improvement, actually, even in some of the results that I have shown today. Let me go back quickly. Yeah. Yeah, so some yeah, actually there's no good example here, but anyway, you see that there is a difference between version 4 and version 5 here, because in version 5 is being applied like a different optimization for Kepler and Fermi. In the case of Maxwell, these two codes in reality are exactly, or if not exactly the same, very similar, is because they both use shuffle instructions, and as you see, the performance doesn't change, right? And other optimizations were still useful for previous architectures when you start using shuffle instructions, because they are way faster than going through the shared memory. You can see that I mean, there is no improvement from version 4 to version 5. Yeah, I don't have better examples today, but because hopefully we will talk about the warp shuffle instructions again soon, we can clarify a little bit more. But thank you very much for the question. I think it was a very interesting observation.
Okay, thanks. And I have another question.
Yes.
Like on slide, I think it was 25 or around that.
Mm-hmm.
It looks like whenever a warp writes to the local registers, it also writes the same to the shared registers.
You mean this one?
Yes,
this
exactly.
Slide?
Yes.
No, I mean, so this is this is a way of explaining how we access the shared memory, right? So there is one value in shared memory here, this shared memory bank, that once, I mean, is needed by the thread being executed here in this lane or this processing engine 0. So the way of accessing it is through this interconnect, as you see, and then we write it into our register, right? So this is essentially a load operation or a read operation from the shared memory bank to the register. So you said that there is kind of double writing here.
I'm not sure. Are those at the top? Are those multiplexers? Like, do we decide if to write, whether we write to the local or to the shared register, or?
Yeah, I think so, exactly. So here I guess that this is to decide whether you want to write here or you want to write here. Yes.
Okay. And what's in the shared register has nothing to do with what's in the local register, right?
What do you mean by it has nothing to do? They are different. It's a different. It's a different memory space. That's for sure.
Okay. So what's in the local register could be completely different from what's in the shared register.
Yeah, of course. You can have completely different values. Yes.
Okay. Okay, thank you.
Okay, yeah, thank you for the questions. Are there any other questions? Okay, yeah, I'm going to see it. I also don't see any questions in the YouTube chat. So I think that we are done for today. As usual, thank you very much, everyone, for your attention in Zoom and in YouTube. I hope you found this lecture useful. We will continue with another parallel pattern in our next lecture, and hopefully you will find it also interesting as well. Thank you very much, everyone, and